Okay, now we're looking generally at rational functions, and a rational function, as you can probably guess, is a ratio of functions. From the word rational, of course, that's what it means. And all we have to concern ourselves, thankfully, is just a ratio of linear functions. So if we have a linear, and notice I'm using two different colors here because we would expect our linear functions to be different, of course, otherwise their ratio would be 1. And we'd be graphing a horizontal line y equals 1. So if we have a linear function 3x plus 5 as an example divided by another different unique linear function x plus 1, that's what we can call a rational function. And believe it or not, this thing here in purple is just a reciprocal function in disguise, a transformed reciprocal function. So how does one go about seeing that? Well, I'm going to show you the trick first. And maybe before I show you the trick, let's look at the most obvious part of this. We know where our vertical asymptote is, because our vertical asymptote is always where division by 0 is created, and of course that happens at x equals -1. I cannot input -1 into this function. I'll have division by 0, so that means our vertical asymptote has to be at -1. And that's not a trick, that's exactly the same as what we've done in the last couple of videos. The line's a bit crooked, but I'm sure it will suffice. So there's our vertical asymptote location. Okay, so now for the trick. The horizontal asymptote is always just your x coefficients. So of course we have a 3x on the top and we have a 1x on the bottom. So guess what? The ratio of those numbers is 3/1. That's where a horizontal asymptote is located, of course, and that's going to be 3. And we'll notch this out, of course. So you probably are asking yourself, well, that's great, tricks are useful, but why does that work? Well, let's take a few moments to explore why that works, and then in the future, just memorize it and know that if you're looking for your vertical asymptote, there's nothing new. Just whatever makes the denominator equal to 0 is the location of your vertical asymptote. The new thing that you have to memorize is the use your x coefficients will tell you the location of your horizontal asymptote. So why does that work? Well, we're not going to learn how to divide, use long division with algebraic expressions in MathSL, but what we can do is, I guess rewrite this first. Was it 3x plus 5 all over x plus 1? And it's probably not a shock that if we did learn how to divide x plus 1 into the top, that it's probably going to require us dividing it in 3 equal times, because 3 times x, of course, is going to give me 3x. So that's a little bit of a hint. So on the top, I'm going to recognize that if I had 3x plus 1s exactly, right, I could divide x plus 1 into that 3 equal times. But of course, I don't have 3 times x plus 1, because if we think about that, that's 3x plus 3. And I have 3x plus 5 up top, so I have to put another plus 2 here. And now I have algebraically the same thing as I had originally. So I'm recognizing that if I have 3 multiples of x plus 1, that's 3x plus 3, an additional 2 gives me the plus 5 that we had originally. Okay, so how's that going to be helpful? Well, because of this plus right here, this one, we can split this apart into 2 fractions with the same denominator. So this is going to be y equals 3 times x plus 1 all over x plus 1 plus just 2, constant 2, over x plus 1. And check this out. That divides in evenly, and all we have left with now is 3 plus 2 over x plus 1. So this is mathematically the same thing as what we originally had up here. And we kind of sneakily divided our x plus 1 into 3x plus 5 just by relying on a little bit of common sense and a little bit of trick by creating that exact multiple of x plus 1 first. And I think that should be pretty easy to follow. But keep in mind, the whole purpose of that was to recognize that this constant at the end, of course, is our horizontal asymptote, which we got from the shortcut. Remember, in the future, please use this shortcut of dividing the x coefficients. And notice our vertical asymptote is still x plus 1. Now what's nice about this form, if you did go to the trouble of doing this, which honestly I don't expect you to, especially during an IB assessment, is this also shows us that we have a vertical stretch here as well by a factor of 2. And if for some reason you're not seeing that, we could quickly scribble that down again, recognizing that this is 3 plus 2 times 1 over x plus 1. And then that's, typically the way a vertical asymptote, vertical stretch would show up initially before you multiplied it through. Okay, so if we know there's a vertical stretch by a factor of 2, that would help us sketch our basic reciprocal function, which is sitting here with a vertical stretch by a factor of 2, and then we could simply just place those points, stagger them around our asymptotes there. But of course, if that's something that you don't know because you didn't bother doing that little algebraic manipulation below, then how are you going to get some points on this curve? And hopefully you're saying to yourself, well, I can just plug in some x values and get some y values. So when x is 0, all this is gone, and I'm left with 5 over 1. So 1, 2, 3, 4, 5. There's one ordered pair. And if you want to plot more points, you can of course plot as many as you want, but usually 1 or 2 in each branch would suffice. So if I put x equals 1 in, I'm going to have 3 plus 5 on the top, and we're going to have 2 on the bottom, which is 4. And you can start to see that this is our crooked basic reciprocal function that's actually stretched by a factor of 2. And even if you don't know that, this will still suffice by plotting at least 1 point on that branch. Okay, so let's do a couple of other, and if you're not really following what I'm doing here, I'm just doing a table of values without keeping a strict track, I guess, of everything that we're inputting and outputting. So if you want to do that, of course, be my guest. So let's put in, of course, we can't put in -1, so let's put in -2 as an x input, and that's going to give me -6 plus 5 over -1, over -1, and that gives me -1 over -1, which is a positive 1. So there's our next value, and you can see there's more evidence that we do have that vertical stretch by a factor of 2 that that I showed you below. So one more ordered pair, and we are done of this transform function. In disguise, how about -3? So if I put -3 in as an x input, I get -9 plus 5 all over -3 plus 1, which is of course -4 over -2, which is going to be plus 2. And there we have it. Our rational function. And that's pretty choppy, so again, you can, unless you find this entertaining, which some of you might, you can fast forward through me bumbling around with my tablet here. Okay, so there's our second branch. And of course, try to avoid your vertical asymptotes and your horizontal asymptotes there as well. And clean this up. Okay, so just to summarize, we started off very quickly. We started off with a ratio of 2 linears, and that actually was a transform reciprocal function in disguise. Now, whether you go through that trouble or not, I'm not sure if you need to. What I want you to recognize is how to find your horizontal asymptote, and then after that, you should know where your vertical asymptote is, because that's not new, and then just plug and chug in some x values, get some y values, and then you'll see your basic reciprocal function starting to take shape. Sorry, I should say your transformed basic reciprocal function taking shape.